Hi guys, welcome to Learning Electronics Repair. Today we're going to look at the most common faults on electronic equipment. This will apply to any electronic device, to be quite honest, whether it's something like a tablet, a graphics card, a PC, a laptop, whether it's audio equipment, whether it's industrial electronics. We're going to look at the most common failures. So this should give you a good idea when you're trying to repair something, maybe something you've never tried to repair that type of device before, what to look for first. Where do I start? Okay, so these are the most common failings you will find. There are 12 of them, but because I go into quite a lot of detail here, so not only what the faults are, but what is the likely causes of them, how to deal with that type of fault, how to repair that type of fault. The video is going to get too long. So this is part one. These are the top 6 causes of failure in electronic equipment. So, number 1, power devices. Power devices are usually found on the output of a device. So in the case of this amplifier, we have output transistors. That's these large things here. We also have some more smaller transistors you can see. But power devices not only transistors or MOSFETs. It can also be things like SCRs, thyristors, triacs. Anything that is driving some device. And these are very common failure points. Quite often these will be mounted to heat sinks like we see in this case. Or again on here the power devices are underneath this heatsink. But they may just be mounted to the PCB. So here is a motherboard. And these MOSFETs are power devices. Now in this instance, they're not driving something external to the PCB. These ones are providing power to the CPU at a low voltage and high current. So they are still power devices. They are part of a power supply. It's just in this case the device they're driving is on the same PCB. So why do power devices fail, and how should we deal with the situation if we find a faulty one? Normally speaking, if the device is operating correctly and it was designed correctly, so the components are running well within their tolerance, these components shouldn't fail. These should last for the entire lifetime of the device. But they are common failures. Why? Well, often because of 2 reasons. One is abuse. So in the case of this amplifier, this may have been overdriven. So effectively, some operators have been driving this amplifier above its rated specification. So that's one common reason for these to fail. Another reason, as I just mentioned, could be bad design. If you have the most powerful or power hungry processor for that platform, you may be pushing these, which are powering it, to the limit. And in that case, they may just fail, okay? Yes, we can have abuse, short circuit CPU. That may well cause them to fail. Another good example would be in the case quite often of triacs. So these are effectively mains switches, and they're driving things like heater elements and such like, okay? If the heater element fails, then the device will fail. We have power devices driving motors. If the motor seizes or something goes wrong with the equipment and the motor jams or something mechanical happens, or maybe the motor wiring is just burnt out, then that will cause the driver devices to fail. Normally when power devices fail, they do one of 2 things. They either go short circuit or they go open circuit. The ones that go open circuit are usually visibly open circuit because they explode. Finding short circuit power devices is generally not difficult. There are challenges in multi-phase circuits like that VRM on the motherboard I was showing you, and I've made videos about that, so I won't specifically go into it. But once you find short circuit power devices on an output, you should do at least 3 things. 1, obviously remove and replace the devices. But before you try this again, 2, have a look to see what is driving those devices, because the chances are, if you have a short circuit in the output device, which is often operated at high voltage and certainly high current, but the high voltage can then go back into the circuit to whatever is driving it and cause a failure there. So you need to work your way back from the short on the output that you find as far as you can until you find components that are no longer damaged. Another option, if you're not sure, when you replace the output devices, replace the driver devices. If there's an IC controlling this, or a lower powered transistor and then an IC, and if they're not expensive, just change them. The other thing you should really try is maybe slightly less obvious and maybe more difficult, but you should also check what the device is driving. In the case of this amplifier, is the speaker itself short, or the windings burnt out, or completely seized? Yeah, because that's what's caused it to fail. And although you check all the drivers and the output devices, you plug it back in and it fails again. Yeah. Specifically, you'll find that in cases where the amplifier is integrated into a speaker, an active speaker. The same with a heater element. If your PCB has come from a coffee maker and one of the triacs is short circuit or open or blown up, you need to find out what that is driving and then go and check the heater element or the wiring in the coffee maker. Is there a short circuit somewhere? Has something overheated? Has something failed and then caused your component to explode or just go short? And the same, what is driving your faulty component? Is that okay, or can I just easily change it? So that is really everything about output devices. But there's one specific type of output device I haven't mentioned. I will mention this now. A lot of electronics, power supplies in particular, for example, ATX power supplies and other power supplies, pieces of industrial electronics like this one, this is an air conditioner control PCB, will have a standby supply. And the standby supply commonly is driven by a chip like this one, okay? This is a very common form. You can normally spot them easily. A, because you buy a small transformer, and B, because often there's a leg missing just there, yeah? That divides the high voltage pin from the low voltage part of the device. These will commonly fail. So that is another good place to look. If they fail, they usually go short, often blow the fuse. Sometimes they will go open. So check these devices for shorts. Power your device up with a light bulb in series so it doesn't blow up any more than it has already. And check to see if the low voltage standby supplies are running. There's another common style of these, which are these type of devices, again commonly found in standby supplies, or they could be the main supply for a low powered item, as could that. And surface mount devices like this one we see here, another one here. These are quite commonly near to an inductor coil. These are also power devices. They are DC to DC converters, and these again are fairly common failure points. Sometimes they will also look like that one you see there and there. The reason these fail is usually twofold. One, that there's some problem on the output of the DC to DC converter, so a short in the load will cause this to fail. So if you find these failing, you need to check to see if there's a short on the output. And if you look at the data sheet, you'll be able to figure out where the output is, or if you're more familiar with these circuits, if you measure from the coil to ground, that will also tell you where there's a short on the output. Bear in mind the device as you're driving could be quite low resistance. It could only be a few ohms, depending on what is being powered. But these are quite a common failure point. The other reason these fail is in cases where the device is externally powered like this. So it says it runs on 5 volts on the back there, for example, but that doesn't seem to matter to a lot of owners who will happily, because they can't find the power supply, plug a 12 volt or a 19 volt power supply into this and then be surprised because it failed. Okay, so those are the most common reasons that these devices fail. And before you change the device, make sure you don't have a shorted output. I mean, you may not. Maybe the device has just got a hole in it. Yeah, they do sometimes just fail. So, power devices. Check them first or early on during the repair. That's the place you should go to pretty much straight away, really. And if you find blown ones or shorted ones, then as well as replacing them, look to see what drives them further back in the circuit. Check if you can the condition of the load they are driving, and also if they're short, not only check back in the circuit to see what drives them and make sure that's okay, but check what provides them with power. So in the example of this, I have short circuit transistor or MOSFETs here. Then the power will come via the bridge rectifiers. We see some here, some here. So if these are short, they could be short. That power to them will come through fuses, for example, which we're going to talk about in a moment. Maybe also you'll find thermistors back in the circuit. So basically anything in the current path from the mains coming in via the rectifiers to the devices could have failed as well. Number 2, fuses. Fuses are a protection device. They are designed to fail in a fault condition. So fuses should be, again, one of the first things you test. I mean, for example, on this PCB we have 8 fuses here, but there's also one further back in the chassis that this came from with a big transformer. So fuses commonly will blow, and they may not look like this. Fuses can come in a variety of styles. We have this style, and sometimes these are not fuses, they're low value resistors, but they look very similar. So you can have fuses that look rather like that. If you see ones with like a letter X or Y on them and a few other options, they are definitely fuses, and you can look up those codes. But we can also have circular fuses like these, which at a glance look a little bit like a circular bridge rectifier, but they only have 2 wires. All sorts of plug-in fuses that you can see. These are fuses, and these are also fuses. So fuses come in all different styles, okay? A couple important things to always note with fuses. If a fuse is failed, especially if it's gone black inside, like the thing is blasted, then that is certainly caused by something else, usually by a short circuit, probably in those output devices we were looking at. So a blackened fuse will be for a reason, it'll be a short. One which is just broken, you can see the wire inside is just broken. Sometimes they just effectively give up, and you may find the device works once you replace the fuse. It could be caused by something that was connected to the device, of course, and now it's not connected. Replace the fuse and it works. So with fuses, if you find a faulty fuse, then it's probably caused by some other fault, and always replace the fuse with the correct type. Don't solder a piece of wire in there, okay? Not only is it bad workmanship, but that device which you have now botched could go out working and set on fire when it's connected to the external equipment that caused it to fail in the first place, and you could get somebody knocking on your door. So don't go down that path, guys. Last thing about fuses, often when a fuse fails, it's visible. These look okay. Look okay isn't the same as is okay. So just bear that in mind. Always test them with a multimeter. Make sure they read short, which is short if it's a good fuse. Number 3, heavy components. Physically heavy components. So on a board like this one, we have a large inductor here, another large inductor here. We have some big capacitors, physically big. These devices are prone to not failing, but fracturing the soldered joints that connect them to the PCB. So in the case of this air conditioner board, there's a lot of vibration. The fans are spinning, for example, the compressor is running, And the vibration over time, mixed with the actual weight of the component, can cause the solder connections to fail. So where that component is soldered to the board, you end up with what's called a dry joint. Dry joints typically look something like this. So we can see we have like a circular fracture around the joint itself. Here is another example. Sometimes they can be very fine like this and difficult to see. Use a microscope or some sort of magnification to help you. Here's another fairly typical one. So you can see numerous dry joints on this one, including these that are fractured sideways. Yeah. So this is the sort of thing you need to look for. Again, quite a fine one, that one. And this one, look, you can see here, is also fractured. Sometimes they may not fracture all the way round, but they're going to fail fairly shortly. So a common place to find this is around heavy components, especially in devices that are subject to some vibration or G-force. So auto electronics is a very good example. And things like amplifiers and mixers, audio equipment that's used in the field, mobile discos and carnivals, this sort of thing. So that's quite a common failure. And you should always have a look around the heavy components to see if you have this sort of problem. This is an easy fix. Firstly, it is just a visual check, which won't take very long because you're not having to look everywhere. And secondly, all you need to do is apply some flux and some fresh solder with your soldering iron, and you've fixed it. You can get these sort of failures on small components as well, but it's just less common. But never say never. And of course, that brings us to number 4, physical contacts. So this covers some obvious things like switches, relays, cables. Sometimes the cables are failed, not the PCB, okay? And some may be less obvious, but IC sockets, especially on old electronics, tend to tarnish, and although it looks okay, you don't have a connection correctly onto all the pins of the IC. And maybe even less obvious, but very common, trimmer pots. Sometimes they close like this, sometimes just an open track with a metal slider, which you can see. These are prone to failure, especially old ones. And these have a metal slider which makes a contact with the carbon track. Here is an example of a trimmer pot with an open construction, so you can actually see the metal slider which is pressing against the carbon track. These are particularly prone to failure, again, especially in old electronics. You'll commonly find them in amplifiers, but also in a lot of industrial type PCBs as well, and sometimes in power supplies where they just preset the voltage. And then there's the big brother of this, or should I say big brothers. So potentiometers, often found in audio equipment and mixers, but could be in other stuff, vintage test equipment and such like, okay? And the other style, the slider, so inside there is a carbon track, and this basically moves a brush along, which moves across that track. So these again have a physical contact, and they are quite prone to failure. These ones in particular in audio mixers, because of the design, which effectively is open, it's very easy to get dust inside there, and the dust acts like sandpaper when you move the slider. So not only is the dust effectively making the connection worse, it's also wearing away the carbon track, and after a short time they'll fail. So these are very common failures, along with the trimmer pots. You can try switch cleaner in these, but most likely your best bet is just to replace them. And the same goes with this type. And bear in mind, particularly in amplifiers, there'll be one of these which balances the output of the amplifier, the offset, so that when there is no signal coming in, the output transistors are basically idling and the output voltage is basically 0. If they fail, then they can quite often take the output transistors with them, because all of a sudden there's a big offset voltage, and the output transistors and the ones that drive them, and maybe the ones that drive those, can fail due to one of those. So they are something definitely to keep an eye on that will fail. The same applies to physical switches, on-off switches and such like, push button switches, toggle switches, especially the ones that are carrying a fair amount of current, can and will fail. Again, you may be able to clean them. Relays, once again, the contacts will fail. Generally, you just have to replace the relay. A very common failure with switches is in vintage audio amplifiers. These are home amplifiers mainly that have multiple inputs, so you can switch between tuner, CD, phono, auxiliary and various inputs. They have large multi-pole switches in them, sometimes with 12 poles, can be a lot of poles, and on those sort of amplifiers also the mute switch may have many poles, and they also tend to fail. Now they fail with age, and if you open one up they're all blackened inside. The only real way to repair those is to actually unsolder the multi-pole switch from the board, for which you need something like a vacuum desoldering gun to be able to do it. Take the switch apart and actually get to the metal contacts themselves and clean them, yeah, with something not too abrasive. Put it all back together, because you can't get those switches. Maybe if you're lucky you have a scrap donor, but the chances are the switches are in much the same condition as the one you're trying to replace. And I have done this sort of work. This is more what I would class as restoration than repair. It takes some time but can be very satisfying. So switches, yeah. Connectors also have physical connections. They're connectors, yeah. Quite often the problem can be in the other part that fits onto there. So basically a problem here, usually again where there's a quite bit of current going down and it starts to arc and it'll blacken the connector. The only real way to fix this, if you can't replace the thing, you need the tools to extract it and clean it properly. Don't think you're going to do this easily with switch or contact cleaner, or replace this if you can, yeah. Same with these type. Another common failure are these type of connectors. This is an IDC, or insulation displacement connector. So basically the way this works is this part, which actually broke taking this one off, it appears to be glued just here actually, or maybe it was just me not doing it very well. Okay, so this part is like a cover, and then we have another cover here. Okay, and then we actually have the insulation displacement itself. So here we can see that each pin in the connector has, it's like a little tuning fork type thing, okay? You can see there, you can see there. So it has like two prongs and a gap in between. So when you clamp this together, and you need to have a proper clamp to do this really, but you can do it with a large pair of pliers if you're careful, yeah? When it's clamped together, the cable is pushed onto that. This cuts into the insulation and makes a contact with the conductor. So that is the insulation displacement. These are quite common to fail, especially ones that are being plugged and unplugged, or maybe even just because you were repairing something and unplugged them. As well as computer cables like this, we'll quite commonly find these on audio amplifiers and mixers. In the case of these failing, you can meter through and find the bad one, but most likely the only way to fix it is actually to replace the ribbon cable. Or if you can get another connector and there's enough space, just cut this off and clamp it a little bit further back. Okay, so those are IDC connectors. A little bit more about connectors, another less than obvious one. Jumpers, yeah, well, jumpers, you find these on lots of circuit boards. With age, they will tarnish and you'll have a bad connection. So that is another one to look out for. And crimp-on type of connectors as well. These usually don't fail in themselves. I mean, you may have a problem with the crimping where the wire comes in. But what's more common with this sort of connector, and this applies to all, by the way, is back to this thing about dry joints or fractured soldered joints. If you're plugging these on, what's likely to go wrong, or just go wrong anyway, is the spade terminal that this fits onto, which is soldered to the PCB. Because you're pushing it, you'll fracture the joint, or maybe again just due to waggling, due to vibration, or fracture the joint. So have a look under these sort of connectors, and for that matter, any sort of connectors for fractured joints, okay, where it solders to the PCB. You may think we finished talking about connectors, but we haven't. So connectors that connect to the outside world, yeah, prone to failure. Sometimes they will tarnish, corrosion, because they're facing the elements basically. Again, quite prone to dry joints and fractured joints, especially things like coaxial power connectors. These type of things and the sockets they plug into. Again, if the device is being plugged in and unplugged on a regular basis, you'll very commonly find that there's a dry joint on the connection between the socket and the PCB, and sometimes a fracture in the wire here where it comes in just because it's been, you know, plugged and unplugged many times. Metal fatigue will set in, so that's a very common failure. On the same basis, not only coaxial power connectors, but jack sockets, corrosion inside them, fractured joints here, or problems with the actual jack plug where the lead's connected to it. USB, HDMI, these are prone, okay, to the same failures, but the most common failure with these is user failure, because the user has plugged the thing in hard, forced it to go in when it's not located right, and they've bent pins. That may well short out pins or short them to each other, which in turn may then blow the chips which are connected to these the next time you power up. And on the motherboard, for example, that may well just stop it from booting altogether. Okay, so always worth looking for damaged USBs, especially on laptops, because they're portable, therefore they face a lot more of this abuse than the desktop, for example. Monitor connectors and such like, all the same. HDMI, very easy to damage, and sometimes it's not the damaged port, although it can be. It is again where the HDMI port solders to the board. Okay, these are not difficult to fix, but require some technique and decent equipment. So good soldering iron, something like a T12 or a C245, hot air in a decent hot air station, because often you have to put a lot of heat into these boards, good flux, good solder, basically leaded solder is by far the best. And on the topic of connectors are these things. So you will find these in vintage audio equipment from the 80s and 90s. I know quite a lot of guys out there, you probably, like to repair and restore this stuff because they just sound great. These connectors are horrible. So the top is not a plug. This is like a little plastic insert which you lift upwards to release the cable. So the cable, the ribbon, each strand or core is a single core stiff piece of wire, and the cable itself forms the male of the plug. Okay, so you lift the little insert bit out and you pull the cable out. Usually they're fairly stiff, they come out, and all seems fine until you come to put this thing back together and they just loose. Although you push it all back together, the thing flaps around, you don't have a contact anymore. I have worked on this stuff, and this looks like a faulty one, which somebody's showing you what can go wrong with these. Okay, the only way I found to repair these is to buy plugs and sockets like these. They have the same pitch, 0.1 inch, like Vero board. Those connectors I was showing you are that pitch, and they come with like rows of pins, and you can solder a pin onto each wire in the ribbon and then fit a proper plug, and then you can plug them in and out. Those connectors are prone to failure just due to corrosion with age. Bear in mind that equipment is probably 40 years old these days that you're trying to work on. or they will fail just because you had to dismantle the equipment to repair another fault. So that's, in my opinion, is how to deal with those and what to look out for. Connectors, a very, very common failure. Either the connector itself, the cable, or the connection to the board, the soldering. On to number 5, capacitors. Some people are going to say capacitors is number 1, but I think there are some provisos with that. And to be quite honest, I would say capacitors are not the number 1 cause of faults that I find. And it's my video. Okay, so capacitors. The reason people feel that capacitors, and in particular electrolytic capacitors like these, fail, and these have failed or are failing, by the way, so you can see this one, which is a new one, has a very flat top, and these are bulged outwards. Like this, if we just get to an angle there, so these are like domed. Okay, this is a capacitor that is failing, and quite often they're worse than that. You will see a brownish colour residue because the electrolyte has leaked out, and sometimes it leaks from the bottom, so there's a rubber bung, if you like, in the bottom where the leads go in, and that fails and the capacitor leaks out onto the PCB. Now, the common misconception that electrolytic capacitors fail with age really is not correct. You will often find old electronics with capacitors from the 1970s that are absolutely fine, and you'll often find devices, especially things like motherboards is a very good example, from around the very end of the 90s, the year 2000, 2001 or thereabouts, where all the capacitors have failed, but they're newer. So this is not to do with age. This is related to industrial espionage. Basically, this is called the capacitor plague. You can go and look it up. And around that time, at the end of the 90s, basically some employees left a capacitor manufacturer, one of the large ones, and stole the formula for the electrolyte, which they then sold to the company's competitors, who, not having the development and research costs, could produce the capacitors cheaper and undercut them, and manufacturers of circuit boards obviously bought the cheaper capacitors. The problem was the formulas that were stolen were not complete. Some parts or compounds, chemicals in there, were missing. So those capacitors, after a period of years, failed. And this is, as I mentioned, known as the capacitor plague. So yes, in a certain age of electronics, you will find faulty electrolytic capacitors is a major problem, but outside of that era, not really. So when it comes to capacitors and failures, apart from the capacitor plague, some important factors are A, the type of capacitor that we're talking about, B, the working voltage and specifically how close to its maximum it is being pushed in the device, and thirdly, the frequency that they are working on. So large capacitors like these you'll find in amplifiers, for example, but also in pretty much all mains powered equipment. These are 63 volts, 12,000 microfarads, and these are smoothing the input voltage. So the voltage is coming in via a linear transformer running at 50 hertz or 60 hertz, depending where you live. That's rectified by the bridge rectifiers we see here, and the output of those rectifiers is smoothed by the capacitors. Because effectively the rectifier doubles the frequency of the incoming mains, these are running at 100 hertz or 120 hertz. And these sort of capacitors generally don't fail. I have seen them fail. I've seen the innards leak out from the back end of them, the bottom, yeah, and quite often rot the PCB while they do it. But these things are pretty reliable. More likely to fail, for example, on amplifiers where you have a plus and minus 95 voltage rail and the manufacturer fitted 100 volt rated capacitors. So yes, a 100 volt rated capacitor can probably handle 110 to 120. There is some tolerance in there, but they're being pushed very close to the limit. And gradually with age, they are more prone to failure. The more likely failure with electrolytic capacitors are ones that are used in DC to DC converters. We have one here. You see the inductor coil. That tells us this is a DC to DC converter, a buck converter. And this is dropping the input voltage, whether it's 5 volts or 12 volts on this graphics card, down to maybe 1 volt or so, thereabouts for the GPU chip. That's drawing quite a lot of current. And these capacitors are running at high frequency. So this circuit is switching hundreds of kilohertz, maybe into megahertz. So these capacitors were just smoothing the output of this. There's the rectifier diodes, probably. And run at high frequency, and these are more prone to failure. Fortunately, when these fail, it's usually visibly obvious just by looking to see if they've bulged or leaked. Sometimes they can fail without visibly showing that they failed. I mean, it does happen. I would say if the things are bulged, they're faulty. If they're not bulged, they might be faulty. But it's less likely, okay? Other types of what you may consider to be electrolytic capacitors, which are these ones, solid electrolytic or polymer capacitors. These are not prone to failing in the same way. Again, we see more of them here. This is a VRM or voltage regulator module with multiple phases firing in sequence like a Gatling gun basically. These capacitors are less prone to failure. And specifically on this one, in fact, these are on the input of the circuit, so these are not subjected to the high frequency noise. The output capacitors in this one are these things. These tantalum. These don't tend to fail, and certainly not in the same way. So capacitors are not so unreliable really. The capacitors which fail like this and worse generally fail in such a way as the capacitance decreases maybe to half its rated value or less, and the ESR, equivalent serial resistance, which you need an ESR meter to measure, goes up. Okay, so high frequency switching circuits, those capacitors, especially from that era around the year 2000 plus or minus a couple of years, is where you're likely to find that problem. Other common failures in capacitors which I've seen are these type of capacitors, sometimes larger than that. You'll often find one of these in an ATX power supply. They're usually rated from about 250 nanofarads to about 1 microfarad. I mean, this one is a 100 nanofarad. These are often used as a capacitive voltage dropper or divider, and they will fail. Used quite often, for example, to power like a 110 volt motor off a 220 volt mains, and they use these types of capacitors to drop the voltage. They're also used, as I mentioned, in switch mode power supplies, in a circuit called an LLC circuit. It's again subject to high frequency switching, so they tend to fail. And when capacitors fail, these type, the electrolytics and those type, generally speaking, it doesn't damage anything else. So replace the capacitors and the fault will go away. Generally, okay, you'll always find exceptions, but generally speaking. The other type of capacitor which regularly fails are these type. Okay, these are quite large ones, but you can find much smaller ones as well. A lot of them around here, for example. These are called MLCC, or multi-layer ceramic capacitors. That ceramic is like the same thing that your coffee cup is made from. And you know, ceramic is brittle. Yeah, it's brittle like glass. The reason these normally fail is because of physical shock to the device or heating and cooling. So they're in an area of the circuit near to something which is running warm normally, and during power cycling on and off, the thing is warming up and cooling down, warming up and cooling down. And because the ceramic expands and contracts at a different rate to the metal ends and to the PCB, this can cause them to fracture. Now, you might think that a capacitor which fractures, it's got a crack through it, goes open circuit. But in the case of these, they don't, they go short circuit. And that's because an MLCC, internally multi-layer, remember, multi-layer ceramic, is like a wafer biscuit. So you have your chocolate or strawberry flavoured wafer biscuit, and as you know, you have multiple layers of chocolate and wafer. Laid up like this. What happens when you snap the wafer? Well, what will happen is some of the layers will touch each other, because they're now displaced. And if this layer, which is the negative end of the capacitor, and this layer, which is the positive end, now touch, you have a short. So that's why MLCCs go short when they fail. And I would say always, okay? When those type of capacitors fail, and bear in mind these are usually on the output of a power supply, whether it's a high frequency switching power supply or a low frequency one, it will short out the power supply. So this will usually cause all the damage. Depending on the type of power supply and the chip that's driving it, depends how well the circuit was designed. The power supply may just shut down, or these things which are driving it may just go pop. So MLCCs tend to go short. They're fairly easy, at least to find. You have a short, sometimes finding the actual capacitor, and it could be something else causing the short, of course, but finding the capacitor, there are methods. I've made videos again about it. I'll link onto this one because it's quite an involved topic, but those do fail in that sort of way. Other than that, I'd say capacitors are pretty reliable things, really. And number 6 is heat cycling. So I mentioned this talking about capacitors, and it applies to other components besides. Commonly, this applies to these type of chips. These are BGA chips, ball grid array. So underneath here are rows and rows of solder balls which attach the chip to the board. So here's a typical BGA chip, okay, and you can see the ball grid array, BGA. As I mentioned, rows and different patterns of solder balls. Can you see them edge on there? So those solder balls are making contact with the PCB. And what can happen, either due to badly designed PCBs or incorrect operating conditions, blocked ventilation vents and such like, we have the same problem we have with the MLCC capacitors. So the thing is heating up and cooling down, heating up and cooling down. Maybe you don't have a good heatsink compound, it's dried out, so it's heating up even more and heating up faster and cooling down faster because it's not attached to the heatsink properly, which has thermal mass. These sort of failures, again, cause the same sort of stress. So the metalwork and the PCB will heat up and cool down at different rates, which means they will expand and contract at different rates, and that can fracture the connections, okay, the balls. Same applies under these memory chips. These are exactly the same, just less balls than they have. How about that? Okay, that sort of fault is fairly common on these sort of boards. Television controller boards or main boards, motherboards, graphics cards, and to be quite honest, quite a lot of other devices can have these sort of chips fitted. This sort of failure may be intermittent, pushing hard down on the chip or flexing the board may cause the fault to come and go. It may be permanent. It can be difficult to diagnose exactly, and if they do fail, by the way, they tend to fail near one corner, I will mention. In the cases I've found this on memory chips, on BGAs, it always seems to be on one corner, the failure. Without the correct equipment and without the amount of experience you need to learn how to work on this, this is not something that you can easily repair, okay? The best way to learn how to do this and to see if the equipment you have will do the job, and by equipment I'm talking a preheater to warm the whole board up, a good hot air station, or even a BGA workstation, which is the same thing but computer controlled. And you'll probably need re-balling jigs to hold the thing in to put new balls on after you've taken it off. You will need the stencils. Yes, there's some equipment involved and some skills. The best way to learn the skills is on scrap boards like this. Unsolder the thing, learn how to do it without damaging the board, reball it, stick it back on. When you can get to the point where you can actually do that without destroying the thing, and when I say destroying, I mean the PCB, get things like this. So this is an old PCIe graphics card. This has no commercial value. You can get these things actually working for basically nothing or as near as nothing. And you can practice unsoldering the memory chip and then solder it back on. See if it still works. Yeah, take the chips off, put them back on. Does it still work? Take this fan off. Underneath here will be a BGA chip like these ones, but probably smaller. Again, unsolder the BGA chip, reball it, put it back on. Does it work? You can probably find an almost endless supply of these things which are basically working. It's a very useful skill. It's well worth learning to do this, but that's the way to do it. Yeah. Don't blame me, by the way, if this PCIe vintage graphics card becomes a valuable collectible in 15 or 20 years time and you've just trashed a load of them. Wow. Hope the skills you learned were worth it. Yeah, I'm sure they will be. Another common misconception with this type of fault and repairing this type of fault. There are some terms that we hear: reflow, reball and replacement. Okay, and then there is the heat it up with a hot air gun and it'll work again. Now, the heat it up with a hot air gun and it'll work again, often people call this reflowing. But what reflowing means is get this hot enough to melt the solder balls. Yeah, and the technique to use, you have to get flux underneath here, which you can actually do because there is a very small gap. We just put flux here, we get a hot air gun, let it all run underneath. And then again, you need a preheater to heat the board up to somewhere 150, 180 degrees, somewhere in that region maybe. And then use hot air or again a rework station to heat from the top, melt the solder, and to reflow it, really then you should very gently tap on the chip. Okay, and you'll find it just moves slightly then springs back into position. The reason it's springing back into position is the surface tension of the solder, but by doing that little bit of tapping you'll move it a bit and that'll cause the balls to resolder. If you have a fractured joint, that may well fix it. It's easier on smaller chips, it's harder on these bigger ones, plus you need better equipment to get this up to temperature to do it. Okay, but that is reflowing. Heating it up with a hot air gun, just get it hot. When you're heating it, or for that matter putting it in the oven just to get it hot, if you're not melting the solder, you're not reflowing it. Now, the myth about this again is like that capacitor plague. So in the early 2000s, NVIDIA in particular had a problem with the design of their BGA chips, and the problem was to do with the substrate. That's this green stuff you can see here, and the die, that's the thing which actually contains the millions or billions of semiconductors, transistors, or the MOSFETs is there. Yeah, that is the die. And just as the substrate is soldered to the PCB by the balls, ball grid array, this is also soldered to the substrate the same way, but much smaller balls. Yeah, they're called bumps. And what was happening is, due to defective manufacture, and a number of big companies sued NVIDIA over this, the die was heating up and cooling at a different rate to the substrate, and the bumps would fail. Okay, now this is where this heat it up at work comes in. So by heating it, but not to the point where you melt those and then let it cool down, you may find effectively this flexes a little bit and the thing will work. But this only applied to NVIDIA chips of a certain era. Okay, it's not a general technique, and often if it did work, it wouldn't work for very long because you haven't fixed the problem yet. You can't actually remove the die and replace the bumps, by the way. That at the moment, as far as I know, is not possible. So you can't actually repair those type of chips. Reballing, by the way, is taking the chip off, cleaning all the old solder balls on, putting fresh balls on with a template, and then resoldering the whole thing back on the board. That is reballing. So that's the difference between the three, if you wondered. Anything else is just messing around with a hairdryer or a hot air gun. Like anything else with BGA rework, it requires the right equipment and the skills. And again, with this reflow where you're just tapping the chip gently after you've melted the solder, the best way to practice at first on the scrap board like this, if you see the thing springing back, you'll get a feel for it, how far you can hit it, because if you move it too far, you'll end up with shorts on the balls. You have to reball it anyway. And then onto things like those old graphics cards, which are worthless. Get it up to temperature, tap it, watch it springing back, wait for it to cool down. Does it still work? So once again, that is the way to learn this. You will not learn this watching YouTube videos. You'll only learn this by, yes, watch the videos, but then do it yourself.